Hello, I am Junho Lee from Gongju National University, South Korea. Today, I'm going to present the world's first application of a TSUM method for 3D memory subsurface detection and classification. Before I start the talk, I would like to name the co-authors of this paper, Seokjin Na and Junhee Jung from Nextin, South Korea, and Ralph Bunziner from Intel Corporation, USA. In this talk, first, I would like to mention new challenges we are facing in the 3D memory fabrication, especially metrology and inspection challenges during high aspect ratio channel hole etch process. Then I will briefly introduce what we have experienced in TSUM method, which we proposed as a cost-effective, non-destructive, and also fast MI tool for the subsurface defect detection and classification. In the next, I will present how we initially detected the subsurface defects with a near-infrared inspection tool, followed by TSUM data analysis of some sample defects, which gave us new understanding of subsurface defect properties. As Mark Lapidus wrote in an article in Semiconductor Engineering last December, there is a vertical scaling race in 3D NAND. The race seems to be speeding up since Micron released 176-layer 3D NAND in November last year. 3D NAND resembles a vertical skyscraper in which horizontal layers of memory cells are stacked and then connected using tiny vertical channels. 3D NAND suppliers are facing manufacturing and cost challenges, especially from high aspect ratio hole etching process. There are several 3D NAND suppliers: Samsung Electronics, SK Hynix, Micron, and Intel. Suppliers have developed their own 3D NAND structure, which are slightly all different. In particular, Intel's 3D NAND is based on floating gate technology. The figure on the left shows Intel's process flow, and we are particularly interested in the control gate process, which is marked B. The figure on the right shows a cross-sectional SEM image. We can see normal thickness control gate and also thin or short control gate, which we want to detect and classify. We are facing different metrology and inspection challenges from the 3D NAND process, where defects are located inside the device. We need a non-destructive optical microscopy as a MI tool for high throughput and low cost. However, we have conflicting requirements for that to happen. We need a near-infrared or infrared wavelength to look inside the device, but diffraction limits reduce spatial and lateral resolutions down to unsatisfactory levels. Regardless transmission, we need a UV or DUV wavelength to have nanometer sensitivity and submicron depth information if we apply conventional optical microscopy. Furthermore, the model-based approach is rarely accepted due to the long computational time required to model various underlying defects within an already complex 3D structure. In 2008, Atota proposed an optical model-based methodology called TSUM through focus scanning optical microscopy to obtain information beyond the diffraction limits with a conventional bright field microscope. Conventional microscope takes information only from in-focus images, while TSUM gathers information from in-focus and also intentionally defocused images. The TSUM tool is basically bright field microscope. The tool takes multiple images at multiple through focus positions while continuously moving the wafer stage along the optical axis. The accumulated data cube is called TSUM data cube, and its cross-sectional image along the optical axis is called the T-SUM image. Existing T-SUM method extracts nanometer scale sensitivity information by library matching or machine learning method. Both require reference T-SUM data or images collected experimentally or computationally, which are not practical in the most 3D NAND cases. Based on the previous experience in T-SUM, which I am going to brief in shortly, we proposed a model-less near-infrared T-SUM method to monitor the channel hole etch process while meeting all the requirements. In 2016, an near-infrared pattern wafer inspection tool called IRIS was applied to monitor micron-scale through silicon via holes. Although T-SUM studies to investigate TSV were first reported, at the time, we were mainly interested in near-surface defects, and the dimension of interest is micron scale. Last year, we developed an adaptive optics-supported T-SUM tool as shown in the bottom figure. We can scan a wafer surface without moving any mechanical parts, but deforming a mirror surface, which was funded by Nextin and Samsung Electronics. Using this tool, we experienced nanometer sensitivity at visible wavelengths less than 1/50th of the detector sampling distance. We also investigated the modulated T-SUM method to estimate the size or height of surface defects even under optical resolution of the applied microscope on the display panel. We defined the ratio at each T-SUM data cube pixel as contrast to backgrounds as given by signal minus minimum over maximum minus minimum. With the definition of the ratio, we defined T-SUM height or volume. In particular, 50% T-SUM volume means sum of pixels whose pixel values are higher than half of the highest difference. In that study, we found that defect size or height has a high linear correlation to T-SUM data parameters, such as 50% T-SUM volume or 70% T-SUM height, which means that defect size or height can be estimated directly from T-SUM data, even smaller than the optical resolution of the microscope applied. Although the study investigated only surface defects, it can be assumed that the size estimation is still valid for subsurface defects, but the linear scale varies depending on the material properties. In order to monitor the control gate process, 4 wafers were under test. 1 standard, 1 weakly squid, 1 highly squid, and 1 standard wafer after post-etch and clean, which were respectively denoted as CGL-POL, CGL-POL+, CGL-POL++, and ACI-POL. Wafers were inspected at Intel for reference, showing that defects are populated at center and edge areas. As mentioned before, we applied a near-infrared bright field wafer inspection tool called IRIS, both for initial defect identification and T-SUM data acquisition. The principal image acquisition parameters for initial defect detection are listed in this table. I would like to mention that the imaging wavelength is a near-infrared, which can penetrate the inside, while autofocus is accomplished at the top surface via another light source at 660 nanometer, at which most wafer layers or films are opaque. The 3 plots show the defect maps of the 3 wafers, 1 standard, 1 weakly squid, and 1 highly squid, measured with the best matching conditions to reference provided by Intel. We can clearly see that the number of defects increase, mostly at the center and the edges as the progress get more squid. But still, we do not know the defect size, neither on the surface location. The through focus scan was done over the range of -6 to +6 micron with 61 steps, forming T-SUM data cube. Since we apply a model-less T-sum method, we use a differential T-sum data cube. That is, the difference of the defect T-sum data from an adjacent die or that of a golden die known to be defect-free. We T-sum scanned 156 defects. This plot shows the planar locations of the defects on wafer. The left and right figures show through focus and differential through focus images of the same undersurface defect. We can notice the signal to noise ratio of the defects becomes much higher in the differential case. As I briefly mentioned earlier, the model-less T-sum analysis uses T-sum parameters such as 50% T-sum volume or 70% T-sum height defined based on a ratio. The intensity ratio is defined at each volume pixel within the differential T-sum data cube with respect to minimum and maximum intensity values. For example, 50% T-sum volume means the sum of pixels whose pixel intensity values are higher than half of the height difference. In this study, we apply 80% T-sum volume for defining the defect center. The four plots show the ISO intensity surface of the differential T-sum data cube for ratio values 0.2, 0.4, 0.6, and 0.8 of the same defect shown in the previous slide. This plot shows the undersurface optical depth of the defects. The x-axis of the plot is the normalized radial position, and the y-axis is the optical depth below the top surface. In this plot, we found some interesting points. First, some surface defects are still classified as undersurface defect by the in-house surface defect removal algorithm. 2. No defects are found at the optical depths of 0 to minus 0.5 micron, possibly the hard mask area. 3. Defects at different zones are populated at different optical depths. We classified 4 different zones: central zone, inner middle zone, outer middle zone, and edge zone. Around the central zone, defects are populated at from minus 0.5 to minus 1.5 micron. Outer middle zone, defects are populated from minus 1.5 to minus 3 micron. Again, edge zone, minus 0.5 to minus 2 micron. 4. Central zones become wider as the processes becomes more squared. 5. ACI process defects are more widely populated than CGL process defect. There are some other distinct features we found. The left figure plots optical depth versus T-sum volume, and right figure plots T-sum PV versus T-sum volume. From the plots, we can clearly distinguish surface defects in terms of surely optical depth and also T-sum volume. ACI process defects are also distinct in terms of T-sum PV. The two plots plot radial position versus T-sum volume and optical depth versus T-sum volume. We can assume that T-sum volume has a linear correlation to the defect size or size of FG short in some degree, which would be confirmed by future simulation. From the left plot, we can see that T-sum volume becomes bigger as the process becomes more squared, and the largest defects are around minus 1.5 to minus 2 micron area. We reported the first near-infrared T-sum application to monitoring the whole etch process of a 3D NAND fabrication, especially control gate recess process. First, we found that near-infrared imaging can be used for undersurface defect inspection with 840 nanometer wavelengths and minus 1 micron focus offset. However, the identification strategy still could not clearly distinguish surface and undersurface defects. Then we proposed a comparative model-less T-sum method whereby we can estimate some physical properties based only a differential T-sum data cube. Applying this method, we found several interesting properties of the undersurface defect solder process. Thank you for your attention.